This is the first of 3 lectures from Chapter 13, all about acids and bases. And this first lecture will be a general introduction to definitions of acids and bases, what we call conjugate acid-base pairs, and a reminder, kind of refresher of how to calculate pH and pOH. And just on this first page, I love learning about acids and bases because they are all around us in our life. It's very common to have acids in food items. It gives it kind of a tangy, sour, sharp flavor. It's common to have bases in cleaning supplies because they dissolve greases. Bases play a role in the formation of stalactites, stalagmites. These are kind of related to each other. And then, of course, acid rain is a continuing problem for us as it erodes statues, which are made of bases, by the way. So acid rain just kind of reacts with them and they're disappearing. So anyway, acids and bases are really important in our lives. Again, the first few slides are going to be a review. An acid is a molecule that has a hydrogen atom directly attached to an electronegative atom. Okay, so if you look at all these acids, in order for a hydrogen to be acidic, it's got to be bonded directly to some electronegative atom. So that's why you wouldn't see CH4 methane referred to as an acid, because these hydrogens are attached directly to carbon, which is not electronegative. Okay, so that's what distinguishes an acidic hydrogen, acidic proton. Classic definitions of acids and bases started with Arrhenius, a guy that first noticed the trends of the properties of these substances. And he defined acids as producing hydrogen ions in aqueous solution and bases as producing hydroxide ions in aqueous solution. The Arrhenius definition of acids and bases covers 90 to 95% of the known acids and bases, but it does leave a few bases out that don't quite fit into his definition. And so sometime after Arrhenius, we came up with an expanded definition, Bronsted and Lowry, 2 gentlemen. And the definition of acid remains about the same as the Arrhenius did, that an acid is a proton or hydrogen ion donor. Let me just pause for a minute. I am actually telling you, if you're not already aware, that a hydrogen ion is in fact a proton. And so real quick, if you look at a hydrogen atom, inside its nucleus is 1 proton, and then outside the nucleus is 1 electron. So if we talk about a hydrogen ion, what have we done to get that ion? Well, we've essentially removed its 1 electron. And so what do we have left? We have left just 1 proton. So hydrogen ion is in fact one and the same with a proton. All right, so then the Bronsted-Lowry definition of a base is the one that made the change versus the Arrhenius. Now, instead of saying a base is something that produces hydroxide ions, Bronsted-Lowry definition says a base is simply a proton acceptor. So you have an acid that donates protons or hydrogen ions and a base that accepts them. What substances does the Bronsted-Lowry definition let in as a base that were not considered a base under the Arrhenius definition? So mainly the bases that are Bronsted-Lowry bases that wouldn't have qualified under Arrhenius are nitrogen-containing substances. It's kind of good to be aware that when you see a nitrogen-containing molecule, it's quite often a base. Now that refers to neutral nitrogen. If you look over here at the product, if there's a plus charge, it's no longer basic. It's actually acidic. But if you have a neutral nitrogen, you're talking about a base. So look at NH3 ammonia, for example. It does not appear, just looking at its structure, it doesn't have an OH to donate, so it doesn't classically fit under the Arrhenius definition of producing hydroxide ions, but it can in effect, accept a proton from an acid, and that's exactly what it does in this reaction. So it is in fact a base. Just to let you know that chemists consider the hydrogen ion is essentially equivalent to what we call the hydronium ion. So you will often see me and other chemists asking you, for example, what's the concentration of the hydrogen ion? And other times we may say, what's the concentration of the hydronium ion? And we're really meaning the same thing. So a hydrogen ion is simply, if it's an aqueous solution, it's not going to stay by itself. It's going to hop on the back of a water molecule and exists as the hydronium ion. But for all practical purposes in water, these two species are one and the same. The first thing you'll need to do is to identify acids and bases by looking at them. Sometimes it's going to be obvious because you've seen it a lot, like hydrochloric acid. Other times it may not be so obvious. Water, for example, can act as an acid or a base. So sometimes you have to look carefully at a chemical reaction to ask yourself, how does water behave? And remember the definition of a base. It's a proton acceptor. So sometimes you need to look at the reaction and decide which species has donated the proton and which species has accepted the proton. In this case, water has acted as a base. And you can tell that if you look at the product it makes, it's clearly accepted a proton. Here's another example. An easier way to do this would be simply to memorize, as I said, that neutral nitrogen-containing species are often the base. But if you didn't remember that, you simply look at the reaction. What has happened to the ammonia? It has accepted a proton, therefore it is the base. And in this case, water has acted as the acid. You can see that it has donated one of its protons. And water is actually called, it's a term that we call amphoteric, which means it can act as an acid or a base. It depends what it's mixed with. All right, the second thing you need to do after you get comfortable labeling acids and bases is being able to identify and label conjugate acid-base pairs. So let's look at the definition of these first, and then we'll do a practice problem. A conjugate acid is what is formed after the base accepts a proton. So let's look at the reaction while I say that again. A conjugate acid is what is formed when the base accepts a proton. Okay? So this hydronium ion in this reaction is a conjugate acid. Conjugate acid always comes from the original base. Conjugate base, on the other hand, is what is left over after the original acid donates its proton. So the conjugate base always comes from the original acid. And so now we have something we call conjugate acid-base pairs, which you need to be able to identify. It always contains one acid and one base. So you hook them up. This is one conjugate acid-base pair. And this is the other conjugate acid-base pair. Okay? So as easy as that seems, very, very, very easy to get confused. I would say up to half students mix this question up on a quiz or a test. So it is easy, but you have to really pay attention to make sure you understand how to identify each of these. This slide is rather redundant, so I'm not going to spend much time on it, any time on it, as a matter of fact. All right. So this would be a typical question I might ask you. I might ask you to label the acid, the base, the conjugate acid, and the conjugate base in a reaction. So this is how you would do it. We simply use letters. So A would be the acid, B would stand for base. Look at the acid and see what it forms, or what's left over after it donates. That is the conjugate base. Remember, there's always an acid and a base that are a pair. That is one of the conjugate acid-base pairs. Then, after you identify the base, see what it forms after it accepts the proton. and that is the conjugate acid. Okay, and so here's the other conjugate acid-base pair. Now it's relatively simple to look at a chemical reaction and label all the substances in that. It's a little trickier, it appears, if I were to give you a table of substances. So let's just look over to the left-hand side. All right, so what if I gave you an acid, and try to ignore what's on the right-hand side for now. What if I gave you an acid and said, what is this acid's conjugate base? So if you have a piece of paper or your hand, cover up everything in the right-hand side of the column. Let's see if you can do these. What is the conjugate base? How you would do that is you'd say, okay, what does an acid do? It donates a proton. So then you would write, what do you get when it donates a proton? And that is your conjugate base. Okay? So in each case, if you're asked for a conjugate base, take one of the protons off of the given acid and then write what's left over. That's your conjugate base. Okay, again, whatever your acid is, if you're asked for the conjugate base, take off one of the protons, only one, and write what's left over. Okay? So that's what we've done in each case here. Now I'm going to go in the opposite direction. I want you to look at the substances on the right-hand side, the last three substances, and cover up the substances on the left-hand side. What if I give you a substance and I ask you, what is the conjugate acid of this substance? Okay? I've given you a base if I ask you that. What does a base do? It accepts a proton. So that means that if you're asked for the conjugate acid, you add a proton. Make sure when you add a proton, you're adding a positive charge too, so make sure you get your charges correct. Water, if you're asked for the conjugate acid, that means this is acting as a base. What does a base do? It accepts a proton. So go ahead and give it the proton and write what's formed, and that is your conjugate acid. Do one more. What is the conjugate acid of hydroxide? If you're asked for the conjugate acid, that means this thing is acting as a base. Bases accept protons, so add a proton, and here's your conjugate acid. So hopefully you've noticed from this chart that it can be a little bit more mind-boggling, so that needs some practice. Let's go ahead and give it a try here. Can you identify acid-base, conjugate acid, and conjugate base in each of these? So put the video on pause, give it a try, and then I'll show you what it is. All right, did you get it right? Here's the acid, which means water has to be a base. Now, when the acid does its thing, that is donate a proton, what's left over? So here's the conjugate base. When the base does its thing, and what does it do? It accepts a proton. What is formed? So here's the conjugate acid. All right? And as far as the second one, let's take a look at that. All right, here's the base, and I'm just going to leap now because I see the nitrogen in it, and it's neutral. And so that's got to be the base. Water therefore has to be acting as the acid. And I'm going to look at the base first. What do bases do? They accept a proton. So let's find that. Here it is, when it's accepted a proton, and that is my conjugate acid. Same thing here. Acids donate a proton. So what does it make? And here's my conjugate base. Now the whole reason we're talking about conjugate acids and bases is because many acid-base reactions are in fact reversible. And so if the reaction that we're looking at right now were to go in the forward reaction, the nitrogen-containing substance would act as the base and the water would act as the acid. I want you to look at the reverse reaction. I want you to look at the products acting as reactants. So I'm going to rewrite these products as reactants. This is what every reversible reaction does. The products become reactants, okay, to remake the original reactants. So let's see. So here's the reverse reaction written out, so it might be easier to see. If you look at the reverse reaction, what's acting as the acid and what's acting as the base? They've kind of reversed themselves, okay? So the hydroxide in the reverse reaction is acting as the base, so that's why it's given the label conjugate base. And the nitrogen-containing substance, which now has a plus charge, is acting as an acid, which is why it got labeled conjugate acid. So the conjugate terms are referring really to the reverse reaction. And I'm just mentioning this here because I think this is what you all learn in high school or maybe even middle school, that when you mix an acid and a base, it typically gives you water and a salt. Salt is just the common name for an ionic compound. And so you would be expected to write the products from an acid-base, or often called neutralization reaction. Okay, and so this is a real common example, hydrochloric acid and sodium hydroxide. So they neutralize each other. I want to take a minute and talk about something called the autoionization of water. That is kind of a lead-in to talking about pH. Water all by itself undergoes what we call autoionization. So two water molecules react to give you the hydronium ion and the hydroxide ion. Very, very, very small amounts. But even in neutral water, you end up with 1 times 10 to the minus 7th molarity of both of these ions. So always in water, you have some presence of each of these, and that's really important. That's where the idea of pH came around. Like any equilibrium, there is a K value or equilibrium constant value associated with this, and it is called Kw, equilibrium constant of water. And if you were to write the expression, it would equal concentration of the hydronium ion, which is one of the products, times concentration of the hydroxide ion, and there'd be nothing in the denominator. Why? That's because the reactants, which normally go in the denominator, are both pure water, liquid water, and that gets left out of equilibrium expression. So here's the expression for Kw. It turns out that Kw, as long as you're at room temperature, equals always 1 times 10 to the minus 14. Now remember, the only thing that changes the value of an equilibrium constant is the temperature. So this will always be what Kw is as long as you haven't changed the temperature. So what happens if you add an acid or a base to water? Well, as long as you don't change the temperature, Kw still has to equal 1 times 10 to the minus 14. How is that going to be possible if, for example, we increase the concentration of the acid? The only way K is going to stay constant then is if the concentration of hydroxide goes down. That's in effect what happens. And this is where the idea of pH came about. Since the concentration of these two ions multiplied by each other is always the same, scientists figured they could measure the concentration of the hydronium ion in any aqueous solution, and that would give them an idea of the acidity or basicity, and that's where the pH scale came about. Here's an example. So let's say that we've added hydroxide ion, which is a base, to water, and we want to know what that has done to the concentration of the hydronium and hydroxide ions in the water. So let's say that we know what the hydrogen ion concentration is, so go ahead and plug that in. We can easily calculate then what the hydroxide ion would be because we know what Kw is. So just divide both sides by 3.6 times 10 to the minus 3 in this case, and you can then get the concentration of hydroxide ion. Okay, so that's a pretty simple problem. So it's probably helpful to remember the relationship between the hydronium and hydroxide ion. There is an inverse relationship. As one goes up, the other one goes down. So just as kind of an overview of this Kw relationship, in neutral water, and I think you know that the pH is 7 for neutral, the concentration of hydronium and hydroxide ions are equal to one another, okay, and they're both 1 times 10 to the minus 7th, because what is 1 times 10 to the minus 7 times 1 times 10 to the minus 7? That equals 1 times 10 to the minus 14, which is what Kw is, okay? So as soon as you start to get an acidic solution, which means you have a higher concentration of the hydronium ion, then the hydroxide solution will go down. If you add instead hydroxide solution or basic solution to water, the concentration of hydroxide will go up and the concentration of hydronium ion will go down. So that leads us finally to pH. pH is a measure of the concentration of hydronium ion, and therefore indirectly it's also a measure of hydroxide ion, because you can get hydroxide ion once you have hydronium ion. pH is a log scale, okay, so rather, and simply all a log scale does is it uses the exponent, okay, so the pH of a solution that contains 1 times 10 to the minus 7 molarity of H3O, the pH would be 7. So the pH, any log scale, allows us to write kind of simpler numbers to represent rather than the scientific notation. So that's the only reason. But it is minus log of the concentration of hydronium ion. So what can confuse some people is that the higher the hydronium concentration gets, the more acidic it gets, the lower the pH gets. So you got to remember that relationship. So high pHs are basic and low pHs are acidic. So here's a scale so you can kind of visualize it. So very acidic substances have very low pHs, and actually you can have negative pHs. It's just not really common, but you could have -1, -2. pH values that are high are basic. And what these values come from, here are the hydronium ion concentrations that correlate with each of the pH values. So you can see from this chart that the pH value is simply the exponent of each of these. You will also see pOH, which is pretty much the same definition. It's just minus log of the hydroxide concentration. Okay. You also need to, if I ask you to calculate pOH, it's a matter of just taking the log of a concentration, but you also need to know how to go backwards with that. If I give you the pOH, for example, and I ask you to give me the concentration of hydroxide ion, how do you reverse this equation? Well, the concentration of hydroxide ion would equal 10 to the minus pOH. Likewise, the concentration of hydronium ion would equal 10 to the minus pH. Ooh, bad writing. Okay. Here's a real simple example. And I would recommend, even this weekend, working quite a few pH and pOH problems. Get those under your belt before we get to the really tough stuff. I already have practice worksheets in the in-class worksheet folder in D2L. So this problem is asking you for the pH. It's very straightforward because they gave you the concentration of H3O. And so really in this case all you need to do is plug into the formula for pH. pH equals minus log of the concentration of H3O. And so when you plug that in, here you go. You get the pH of 2.47. And I might ask you, is it acidic or basic? It's acidic. Any pH less than 7 is acidic. Just a quick little note about sig figs of pH values. This first digit in any pH, so digit to the left of the decimal, is from the exponent. It's not a significant figure. It doesn't tell us really anything other than the order of magnitude of pH. So if I were to say how many sig figs does this pH value have, it has 2 sig figs. You only count the digits to the right of the decimal, and a pH or pOH as sig figs. This is just a summary slide. So here's a straightforward problem that kind of goes in the reverse direction, which you need to be very comfortable with. Instead of asking you to calculate pH, this problem gives you the pH value and asks you to calculate the hydronium ion concentration. And so you need to remember the formula for that. That is 10 raised to the minus pH. Don't forget that minus sign. And if you were to do that, you get the hydronium ion is 3 times 10 to the minus 4. Don't leave your problem in the form of a fractional pH value. You've got to go ahead and enter this into your calculator and get it in scientific notation to get full credit for this type of problem. So P and pH, and the reason I'm telling you this is because there'll eventually be a pKa also. The P and pH simply means minus log. That's literally what it means, equivalent to. P, little p, means minus log of. So anytime you see P in front of anything, like let's say pK, that would mean minus log of the equilibrium constant K. So down at the bottom here, pKw is minus log of the autoionization equilibrium constant for water, which is 14. And it's cool, you already know the relationship between the concentration of hydronium and hydroxide ion. That is Kw. It's always 1 times 10 to the minus 14th, as long as you're at 25 degrees Celsius. But now look what happens. That means that the relationship between pH and pOH is always 14. So they add together to give you 14. So if you know the pH value, let's say we have a pH of 3, that means you automatically know the pOH value because it would have to be a number that adds with the 3 to give you 14. Right? So that's just a cool little relationship. Here's a visual of the same thing, and if you look at pH and pOH, they always add together to give you 14. Be careful when you're working with pOH values. It's easy to get confused. They tell you the opposite information of a pH. So while the pH less than 7 means acidic, a pOH greater than 7 means acidic. I like this chart simply because it shows you all the cool relationships that pH and pOH, first of all, always have to add together to give you 14, and also that concentration of hydronium and hydroxide ions, their exponents add together to give you 14. Okay, remember pH and pOH come from the exponent values. It is very easy to calculate the pH of an acid that is strong. So hydrochloric acid is one of the strong acids. And the reason that's easy, remember the definition for pH? pH equals minus log of the concentration of hydronium. Okay? So pH is not asking you about the concentration of the original intact acid. It's asking you how much of that acid was converted to the hydronium ion. But you're in luck because a strong acid, 100% of it's converted. So with a strong acid, if you start with 0.050 molar, you're going to end up with the same amount of the hydronium ion. So if you look down at the bottom, so pH in this case is the minus log of the original concentration of the intact acid. pH would be 1.3. That's quite an acidic solution. Strong base has a similar definition as a strong acid. It's a base that completely ionizes, completely dissociates in aqueous solution. There are 7 strong bases that you need to memorize. Well, there are 7 strong bases, period, but I would like you to memorize them all. all of the group 1 metal hydroxides. So if you go down group 1 in the periodic table, sodium, potassium, cesium, all of those make strong bases when combined with the hydroxide. And then in group 2, which is the alkaline earth metals, it's the heavier metal hydroxides, so strontium and barium. Calcium hydroxide, which is about halfway down group 2, calcium is some books consider it strong and some consider it not strong. It's kind of right on the border. But the higher up alkaline earth metals like magnesium, for example, magnesium hydroxide is a weak base. So it's only the heavier metals in group 2. Here's an example calculating the pH of a basic solution. So it says, what is the pH of a 0.035 molar solution of barium hydroxide? The very first question you need to ask yourself is whether or not the acid or base referred to is strong or weak. In this case, barium hydroxide is strong. Barium is a heavy alkaline earth group 2 metal, and so it makes a strong base when combined with hydroxide, which means the barium hydroxide in aqueous solution completely 100% breaks apart or ionizes into the barium cation and the hydroxide anion. Be careful to follow stoichiometry. If you look at the formula of barium hydroxide, it has 2 hydroxides associated with 1 barium. Make sure then that your reaction is balanced. So the concentration of the hydroxide in solution, once the barium hydroxide dissociates, is 2 times the original concentration of the barium hydroxide, which ends up being 0.070 molar. That is the concentration of the hydroxide ion in solution. So I'm going to go ahead, it asks for pH. I'm going to go ahead and take pOH first. pOH is minus log of the hydroxide concentration, which is minus log of 0.070. pOH is 1.16, but the problem asked us for pH. So now you have to remember the relationship between pH and pOH. They have to add together to give you 14, so the pH equals 12.84, which is a basic solution as you would expect because you added a base. Here's one of those kind of backward problems where they give you the pH and now they're saying what is the concentration, what is the original concentration. HCl is a strong acid again, so we don't have to worry. We know that 100% of it will dissociate into hydronium and chloride, so that's all we're dealing with. And the formula we need here, we are looking for concentration. So the concentration of hydronium ion equals 10 to the minus pH. So what you really need to do at this point is get your calculator out and make sure that you know how to calculate this. Okay, that's messed up more than one person on a quiz or test, not knowing how to use a calculator. And I'll give you the answer on the next page, but make sure enter it and go ahead and see what you get. What is the concentration of a solution of KOH if the pH is 11.6? So I'll give you a little tip here. You're going to start out the same way with the same formula, finding the concentration of hydronium ion. Once you get H3O, you're not done though, because it wants to know concentration of hydroxide. So you need to remember the relationship between the concentration of hydronium and the concentration of hydroxide. Well, 10 raised to the minus 3.75 equals 1.8 times 10 to the minus 4. I'm going to bring back that idea of sig figs again because I want to make sure you understand it. It's going to pop up in one of your labs pretty quickly. So this pH value, how many sig figs does it have? If you remember what I said a couple slides ago, it has 2 sig figs because you only count digits to the right of the decimal. Any number to the left of the decimal simply represents the order of magnitude or the exponent of the concentration. So, all right. So then how many sig figs does the answer have? Well, hopefully you know how to do that by now. That has 2 sig figs too. So keep your sig figs matching each other when you go back and forth from pH to concentration. If one has 2, the other should have 2. So to answer the second question, it's a little bit, involves 2 calculations instead of 1. So working out this second one, the first step is, excuse me, finding the concentration of hydronium ion from the pH. And I have a 10 to the X button on my calculator. And so I would use that 10 to the X button, and you put in X as minus 11.6. And when you do that, you get that the hydronium ion concentration is 2.512 times 10 to the minus 12 molarity. The problem is asking you for the concentration of the hydroxide. And so how do you get that? You remember now that concentration of hydroxide times concentration of hydronium ion multiplied together equals Kw, which is 1 times 10 to the minus 14. So if you're trying to solve for concentration of hydroxide, it would be 1 times 10 to the minus 14 divided by the concentration of hydronium ion, which we just found, 2.512 times 10 to the minus 12. And when you plug that in, you get that the concentration of hydroxide, which by the way is the same thing as the concentration of KOH, the original base, because KOH is one of the strong bases, so they equal, it completely dissociates. This is just more practice, and this is the type of practice I want to have you do this weekend with the skill worksheets in the folder in D2L. It's important just to shake all the cobwebs out and almost have this be muscle memory. So here it's giving you concentration of hydronium. Remember that I said chemists will use these two interchangeably? Okay. Is, let's see, 1 times, I'm going to put it in scientific notation just because, and it wants to know pOH. So I'm going to find pH first, and I know that that is, oopsie, minus log of the concentration of hydronium ion. And I'm not even going to punch that into my calculator since my coefficient's 1. I know that I just grab the negative of the exponent. So pH is 5. And I also remember the relationship that pH and pOH, when added together, have to equal 14. So I know that pOH equals 14 minus 5, which is 9. So that's the answer. There's the pOH for this problem. And I actually forgot during this lecture that I had worked it all out for you. So if my handwriting was too sloppy, there you go. 2 more slides, we're almost done. Here's one more. If the pH is 10.6, that would be a basic solution, right? What is the concentration of the hydroxide ion? You should be able to make an estimate in your head at this point, just to make sure, kind of to double check your answer. If it's basic, you would expect the concentration of the hydroxide ion to be greater than 1 times 10 to the minus 7. So hopefully, if you do it right, you'll get a larger number than that. So let's go ahead and calculate it. Concentration of hydroxide is 10 to the minus pOH, right? But I don't have pOH yet, so I have to calculate it. So 14 minus 10.60, which was given to us, equals, let's see, that would be 3.40. And so now we can plug that into our formula up here. So 10 raised to the minus 3.40. Don't stop here, you won't get full credit. Go ahead and plug this into your calculator and get something in scientific notation. And it turns out that 10 to the minus 3.40 gives you a hydroxide ion concentration of 4 times 10 to the minus 4. That is much greater than 1 times 10 to the minus 7, as it should be in a basic solution, so you're all set. That's it for lecture 1. This is by far the easiest part of this entire unit, but it's the foundation upon which everything else rests. Make sure you're very, very comfortable with it.